I'm going to get started. All right, so you guys are here because you're taking the AP Chemistry exam and you're all stuck at home studying for it by yourselves, and they changed the format of the exam. So I wanted to take a couple minutes to talk about what they changed it to, all right, and what they're not testing. Okay, so first, your exam is going to be, it looks like 25 minutes plus 15 minutes. So 2 questions. They're both of the long free response type. The first one is going to be like a lab-based, analysis question. All right, and then the other one is going to be one of your, stereotypical normal FRQ questions. All right, that's going to be theory-based. All right, so one will be lab-based, one will be theory-based. All right, and I know somebody had a question, so if you want to unmute yourself and ask your question, I will try to have an answer for you.
My question was gonna be with the graphing calculators, but I don't know. Like, what if we don't have a graphing calculator?
I do not know the answer to that question offhand, but I will get you an answer and follow up after the session. I do not know if they require it or they do not require it, but we'll get you that answer. Okay?
Okay, thank you.
No problem. All right. So then, as far as material on the exam, uh, the AP Chemistry has decided that they're going to test everything except for 2 things. All right, they will not test anything that is related to acids and bases, and that includes buffers and titrations. All right, so that takes out a big chunk of material, so this will not be tested. And they will do no applications of thermodynamics. All right, so what I think this means, applications of thermodynamics is somewhat vague, but I think that means that they will not do lab-based questions based on thermodynamic data. I think that's what that means. But when I get more specific information, I will let you guys know. Does anybody have any questions before I get started? All right. Did you guys all receive the 2017 free response questions? You can say yes or no in the chat box. Yeah? Everybody have a chance to glance at them? Ish. Okay. So the way that I think that we should do this is let's just try to simulate what they are going to ask us to do. All right. And I'm going to go over the 2 lab-based questions first. All right. And then we'll go to some of the theory-based questions. All right. So I'm going to start with question 4. All right. Because it is a lab-based question, and that's what we're going to be starting with on the actual exam. So why not simulate it now? All right, so I'm going to go ahead and put question 4 here. And we're going to work through the question, and we're going to work through how, what knowledge we needed to actually approach the question. All right. Everybody have a clear view of the screen? Yeah? Yes? Perfect. Okay. All right, so then protocol here. If you have a question, please either put it in the chat box and I will repeat the question and I will answer it. Or if it's a big mouthful, you can just write, I have a question and need to unmute in the chat box and I will let you, okay? But so let's just try to time that out. Okay, everybody good with that? Perfect. Okay, so I'm going to go ahead and read the question. A student investigates various dyes using paper chromatography. The student has samples of 3 pure dyes, which are labeled A, B, and C, and an unknown sample that contains one of the dyes. The student prepares the chromatography chambers shown above on the left by putting a drop of each dye on the position and standing the paper in a nonpolar solvent. All right, the developed chromatograms are over on the right. Okay, so here is the foundation for this question. All right, the foundation is that we call the paper the stationary phase. All right, and they told us that it is polar. All right, they told us that right here. All right, and so any compounds that are polar will interact strongly with the paper and not interact with what I'm going to call the mobile phase, all right, which is that nonpolar solvent. Okay, so this is the like dissolves like thing. All right, now on the flip side of that, if we have a compound that is nonpolar, it is going to not interact with the paper as well and is more likely to interact with the mobile phase, all right, with the solvent. Everybody with me? Yes? All right, and so what's going to happen is that polar compounds stay near the bottom and nonpolar compounds are going to move with the solvent. All right, and then this is why they tell you where the solvent front is. All right, we are going to measure with respect to the solvent front. All right, does everybody understand the setup of the experiment? Does anybody have any questions? All right, everybody okay? Need some interaction, guys, so I know if I'm going at an okay pace. Perfect. All right, so now here we have our 2 things. We have dyes A, B, and C. We have our unknown. All right, and then I'm gonna look at our developed chromatogram. And now just based on the knowledge, I'm not gonna read the question quite yet. All right, which of these is most polar? Okay, we're gonna say that dye B is the most polar. All right, why is that? Because it is the furthest towards the bottom. Okay. All right, and then which one is the least polar? All right, C. Okay, this one's the least polar. because it interacted with the mobile phase. All right, and went the furthest. All right, and then di A is somewhat in the middle. Okay, all right, and then our first question is, which dye is least polar? Okay, so now we know the answer. All right, so we can say that dye C is least polar. All right, so layup. And now we have to give a reason. So how do we know it's the least polar? All right, we know it's the least polar because why do polar compounds go to the bottom? Okay, so it's not going to be the same with every chromatography setup. All right. Here they told you that it was a non-polar solvent and that the plate here was polar. All right, so if you have a polar compound, it's going to stick to the polar plate and it doesn't want to move. All right, now the nonpolar solvent is going to start inching up the plate, and as it goes up the plate, it's going to drag things that are nonpolar with it. Does that make sense? So if we had flipped this chromatograph and said that the stationary phase, the plate, was nonpolar, and the mobile phase, the solvent, was polar, we would have gotten the opposite results. Does that make sense? So in this case, dye C is least polar because it moved the furthest with the nonpolar mobile phase, all right, the nonpolar solvent. Okay. All right. Does under the like dissolves like, the compound that is nonpolar, so it doesn't interact with the paper as well, and it is more likely to move with the solvent. You'll have to excuse my handwriting. It's a little hard to write on the screen. Okay. All right. So everybody is okay with part A? Great. Piece of cake. All right, so now which dye is present in the unknown sample? You guys like A? Okay, so good. You guys picked the right one. So dye A is present in the unknown sample. All right, and then we need to justify that. They say justify your answer, so we have to justify our answer. So how am I going to justify that answer? So a little tricky because the solvent front isn't exactly at the same spot, right? But here's what we can say. All right, we can say that, if I look at the distance here, all right, dye A is right smack in the middle between where we started and the solvent front. Everybody agree with that? So dye A in the middle, straight in the middle. Okay, so, all right, so now I can say that dye A on the control plate is directly in the middle between the solvent front and the origin. All right, and then on the experimental plate, all right, we can say the same thing. All right, die A is in the same position. All right, it's exactly in the middle between the solvent front and the origin. All right, does anybody have any questions on this question or in chromatography in general? So great lab-based question. No? All right, if anybody has, okay, question, do you want to unmute your microphone? Typing is also perfectly fine. Okay, are we in general looking at the ratio of the distance, or should we actually compare the distance using a ruler? Great. Fantastic question. So this will give me an opportunity to actually show you how you would measure this. All right, so very unlikely you're going to get a ruler on the actual exam. Okay, so what you usually do is measure your distance with what is called a retention factor. All right, a retention factor or RF value. Did you guys learn about this when you did lab? Yeah? Okay, great. What I'm going to do is actually put the picture back up here blank so that I can mark it up again. Okay? All right, so here is my picture. So the RF value is the distance that the spot traveled divided by the distance of the solvent front. All right, so let's just say that I'm gonna break this up and say that this is 1, 2, 3, 4, 5. I can say that die A, the RF value of A, would be 2.5, that's how far it went, divided by 5. All right, that's how far the solvent went, or 0.5. All right, and then if I did the same thing here, all right, 1, 2, 3, 4, 5. All right, then you would say that the RF value is exactly 5. So if you had a ruler, you would do it with a ruler, but I don't think they're going to give you a ruler, if that makes sense. But perfectly okay to use RF value as a way of measurement. Does that make sense? Will the lab-based question have more parts since you get 25 minutes? I would assume that it would be one of the longer questions, yes. Okay. All right. Is everybody, how many parts would I say? I do not know. I have not written the exam. However, the longer questions tend to have 4 to 5 parts. So 4 to 5 parts, perhaps. All right. So the next one I want to go ahead and do is question 5, which is also a lab-based question. Is that okay with everybody? Perfect. For the physics exam, their lab question has us design a lab. Will Chem do this? Sometimes they will have you design an experiment that would support or refute a hypothesis. So that is possible, but is not always the case. I like to tell a lot of my clients that there's no always in chemistry, right? So maybe, but not necessarily. All right, and the best we can do to prepare for this is to take the old free response questions and take your lab manual and, go through the labs and just practice. All right, that's what we're doing here today. Everybody finding this helpful so far? Fantastic. That is what I want to hear. All right. So, a student performs an experiment to determine the enthalpy of combustion of 2-propanol, which combusts in oxygen according to the equation. So thankfully they gave us the balanced equation. So let's remind everybody what enthalpy is. All right, so enthalpy is heat energy. All right, it is commonly referred to as delta H. All right, delta H is our enthalpy. And remember that if delta H is a positive number, that means that we are taking in heat from the environment, from the surroundings. And that would be what we call an endothermic reaction. I also like to think of heat as being a reactant. All right, and then the flip side there is that delta H could be a negative number. This is if we are releasing heat to the surroundings. All right, this is an exothermic reaction. And I like to think of heat as a product here. All right, now in general, combustions are very exothermic, and I would be writing plus heat here as a product. All right, and then probably the goal of this experiment is to figure out how much heat. Okay. All right, a student heats a sample of water by burning some of the propanol that is in an alcohol burner, and we have this set up here. The alcohol burner uses a wick to draw liquid up into the flame. The mass of the liquid combusted is determined by weighing the alcohol burner before and after the combustion. It looks like I forgot to put up the data. All right, so hang on a second. Let me grab the data. All right, there's our data. Okay, so calculate the magnitude of heat energy absorbed by the water. All right, and then they tell us to assume that the energy released from the combustion is completely transferred to water. So that means that we're not losing any of the energy to the surroundings. All right, so we're kind of assuming it's a perfectly, insulated system. All right, and okay, so do you use the MC delta T? I like it. You just killed my punchline. All right, so how do I solve this? So somebody already said we use Q is equal to MC delta T. That's our calorimetry equation. Perfect. Awesome. Okay, now here is the trick. Which mass do I use here? So actually, before we get to this, let me explain what is in the equation. All right, so here, let me define my variables. Q is your heat energy. All right, M is going to be mass, usually in grams. All right, C is what we call the specific heat. All right, this is how much heat a the substance can hold. All right, so its units are joules per gram degree Celsius. All right, and then delta T is your change in temperature. All right, and then because the units of specific heat are Celsius, this is also going to be in Celsius. Okay, and so now the question is, which mass do I use? All right, and so we got two masses. Which one do you guys think we use? So what's actually being heated? So what's actually being heated is the water. All right. So we're going to use the mass of the water. And if we had any question about that, we were only given the specific heat of water. We don't know the specific heat of the alcohol, so we would never be able to solve the problem. All right. So Q here, I'm going to use the mass of the water. So 125 grams. 4.18 joules per gram degree Celsius. I'm going to notice those units drop out. And the delta T here is going to be 51.1 minus 22. All right, and that gives us 29.1. So 29.1 degrees Celsius. All right, and that drops out your degrees Celsius. So Q is then we multiply it all together, and what I get is a big number, all right, and then we're going to talk about significant figures. All right, this is the number that I get. All right, now first of all, we always want to make sure we read the question. They told us that they want this in kilojoules, so I need to take this and divide by 1,000 to get to kilojoules. All right, and then how many significant figures should I be rounding to? Okay, so since we're multiplying, we're gonna take the smallest value of significant figures. We're gonna notice that here I had 4, here I have 3, here I have 3, here I have 3. So I have to take this to 3. All right, so 15.2 kilojoules. All right, and that is our answer. Does anybody have any questions about part A? Okay. Is the whole thing wrong if you have the wrong number of significant figures? Not usually. Not usually. I mean, but if it's ridiculous, then kind of. I mean, if you were to say 15.20475, they would probably mark it wrong. So I would consider that this is not an application, this is just straight thermodynamics. So I think that this one's fair game, otherwise I would not be going over it. Okay. All right. So then the question was, they didn't ask about significant figures in part A, but they did in part B. So would they mark it wrong? All right, I think that's going to depend on your grader. But like the scoring sheet does not mention significant figures, but again, I think they would mark it wrong if it was ridiculous. All right, so if you wrote, 15.20, probably okay, maybe even 15.204, but at some point we stop being able to measure it. Does that answer your question? Okay, great. All right, so let's go on to part B. Based on the experimental data, if 1 mole is combusted, how much heat is released? Okay, so this is a stoichiometry question. All right, so again, I don't think that this is considered an application of thermo. I think it's just considered thermo. But let's go ahead and kind of get going. So does anybody know where to start with this problem? Okay, so what I always tell my students is that you try to start with A, what you're given, and you generally start with things that only have 1 unit. So I was given that I have 1 mole of propanol, so I'm going to go ahead and just stay with 1 mole of propanol. All right, so if I have 1 mole of C3H7OH, all right, now here, note that we have a conversion factor based on this experiment. All right, my conversion factor is that we would have 0.55 grams of your C3H7OH, that comes from here, and then we just solved that you would have 15.2 kilojoules in that reaction. Does everybody see that? So this is your conversion factor. All right, so I'm going to go ahead and convert to grams. All right, so in 1 mole of your C3H7OH, I've got to get grams of that. How do I find those grams? Periodic table, perfect. We get the molecular weight. So carbon is worth 12. So 3 times 12 plus I have 8 hydrogens, which are worth 1. And my oxygen is worth 16, so I have 60 grams. All right, if we're being exact and using the periodic table they give us, it's 60.09. My moles cancel. All right, and now I use the conversion factor that I just set up. 0.55 grams of my propanol gives me 15.2 kilojoules. All right, multiply across the top, divide by the bottom. All right, we'll get a number and then we'll talk about significant figures. Okay, so I just got 1660 point, let's say 7 kilojoules. All right, so now I have to kind of take it to significant figures. So based on my experimental data, all right, how many sig figs do I get to use? Good for you. Only 2 because of this. All right, there's only 2 there. So there's 2 valid answers there's 2 ways to write this. All right. You could either round this to 1700 and not put the point. All right. If you don't put the decimal point there, it is 100% correct. Or you can write it as 1.7 times 10 to the 3rd kilojoules. All right, if you were to put the decimal point there, then that would imply that there's 4 significant figures, and that would be wrong. Okay, so either 1.7 times 10 to the 3rd or 1700 without the decimal point. All right, does anybody have any questions? All right. Okay, last part of the question. A second student performs the experiment using the same mass of water at the same initial temperature. Cool. However, the student uses an alcohol burner containing propanol contaminated with water, which is miscible. Does everybody know what miscible means? No. Okay, so miscible means soluble. All right, mixable is actually not too terrible. All right, so soluble. It means that they can interact with each other and they're totally soluble and you can't distinguish between them. All right, at least just in the mixture. Okay, the difference in the mass of the alcohol burner before and after the combustion in this experiment is also 0.55. Would the final temperature of the water in the beaker heated by the alcohol burner be greater than, less than, or equal to the final temperature of the water in the first student's experiment? All right, what do we think? Okay, so I think about things very mathematically. All right, so when I first did that calculation, I did this, right? Q is equal to MC delta T. All right, and if I had if my final mixture here was water plus propanol, that means that I burned less propanol. Does everybody agree with that? All right, less propanol was burned. So if less propanol was burned, then less heat was generated. Yes? Okay, so less is burned, therefore I get less Q. All right, I get less heat, and if I get less heat, then I have less change in temperature. All right, so the change in temperature should be less. And then as always in any AP statement, you want to make sure that you write because. All right, and then in this case, the because is because the mass of C3H8OH burned was less. All right, does that make sense to everyone? Does anybody have any questions about the experiment? Any of the questions? How do you know that less was burned? Because I'm starting with less. All right, if I have the same, let's say that I have, well, let's try this. So let's say that there is 1 gram of C3H8O6. All right, and that fully reacted. In the second experiment, my 1 gram that I perceived was actually, 0.9 grams of this and, 0.1 gram of water. All right, the 0.1 gram of water isn't going to burn. All right, just the alcohol will burn. We'd be in trouble if water burned. Does that make sense? Is there less because it's mixed with water? Yes. All right. Any other questions before I go on? Okay. So at this point, I'm either going to go back to question 1 or 2, and I don't necessarily have a preference. Does anybody have a preference? No? Okay. All right, so I'll go back to question 1. All right, so that was the end of, the lab stuff that was in this set of free response. So now we're going to go back and do some of the theoretical stuff. Let me mention one more thing. Let's say that just a little test taking strategy here. If you find yourself in a situation where you need the number from B, you need the number from A to answer question B, all right, but you don't know how to do A. Let's say you don't know how to do A, you blank out, and you just don't know, all right? What you do is you write assume answer equals Y kilojoules. No joke. Just assume answer equals Y kilojoules. And then do the calculation here and use Y where you would need it. Okay? Just a little test taking strategy. They will give you the points for B even though you didn't get A if you use it correctly. All right, that's gonna permeate all of the AP exam in this subject. You can also make up an answer as long as you use it correctly. In that case, they probably would not give you points. All right, so I'm going to go back to question 1, and I will just work through some free response questions until our time is done. Okay, so carbon tetrachloride can be synthesized according to the reaction represented above. A chemist runs the reaction at a constant temperature. All right, so it's good if I don't delete the temperature, and a rigid 25-liter container. And then now here we go. All right, chlorine gas Cl2 is initially present with a pressure of 0.4 atm. How many moles are present in the container? All right, so how do I go about solving this question? PV equals nRT. Awesome. Good job. All right, so we'll go ahead and just start the calculation here. PV equals nRT. All right, we're solving for moles. So N is equal to PV over RT, and then we can kind of plug and chug. All right, so my pressure is 0.4 atm. My volume is what they give me, 25 liters. R is 0.0821. I'm going to be careful with my units. They're liters atm per mole Kelvin. And my temperature needs to be in Kelvin because my gas constant is in Kelvin. All right, so my temperature is 120 plus 273 to get to Kelvin. All right, gotta watch your units on these problems. So 285. All right, and so if I solve that, that's not right, Sam. That is definitely not right. 393. Surprise, somebody didn't jump in. Tell me. All right, 393. If I make a mistake, let me know. All right, so 0.4 times 25 divided by 0.0821 times 393. That should give us 0.31 moles of chlorine gas. All right, does anybody have any questions? All right. How many grams of carbon disulfide are needed to react completely with my Cl2? All right, so I'm going to use the answer that I just started with, all right, that I just got as my starting point. All right, so for 2 here, all right, 0.31 moles of Cl2. All right, and then now whenever I want to convert between one thing and another thing, we're going to use my balanced equation. All right, and luckily it's balanced. Okay, so by the way, for the AP, if you see an equation and you don't see numbers, don't assume it's balanced. Okay. You can't assume it's balanced, but if you do see numbers, you can assume that it's balanced correctly. All right, they would not give you an incorrectly balanced equation. That would be kind of mean. All right, so this is balanced. That's great. So they tell us for every 3 moles of Cl2, I have 1 mole of CS2. All right, and then they ask me for grams. So how do I get to grams? Periodic table, I get my molecular weight. All right, and I don't know sulfur, so I'm gonna look it up. So 32.06 times 2 plus 12. All right, 76.13. All right, multiply across the top, divide by the bottom. And I got, how many sig figs do I need? 2, so 7.9. Good. All right. Does anybody have any questions on part A? Fantastic. All right, part B. At 30 degrees, the reaction is thermodynamically favorable, but no reaction is observed to occur. However, at 120 degrees, the reaction occurs at an observable rate. All right, they want us to explain how the higher temperature affects collisions between reactant molecules so that we see a reaction at 120 degrees. Okay, so the AP is going to be looking for some keywords. What words are they going to be looking for? Okay, so what is temperature a measure of? And don't say heat. Heat's not the right answer. Energy, what kind of energy? Kinetic energy? Perfect. Okay, so we can say at the higher temperature, the molecules have a higher average kinetic energy. All right, so they were looking for average kinetic energy. That is exactly what temperature is. All right, so now what does that have to do with anything? Now we have to actually answer the question. So therefore, there are more particles moving fast enough to have productive collisions and overcome the activation energy. All right, does everybody know what activation energy is? All right, does anybody not know what the activation energy is? And don't be shy. Well, I'll define it anyway. Okay, that's perfect. So the energy of activation is the amount of energy that is needed for a reaction to occur. All right, so in order to have a reaction, we have to get over that hump. Okay? All right, I'm gonna move on to part B, part 2. Would kinetic molecular theory apply here? Yes. So, you mean like you want to use the kinetic molecular theory? So they are gases. So yes, this is an application of the KMT. All right, remember that we only get a reaction when things are moving sufficiently fast enough to have productive collisions. All right, but the KMT would assume that all of those are perfectly elastic, but that wasn't necessarily needed to answer the question. So you would still have to say that we have enough kinetic energy to overcome the activation energy. Those were the keywords. But you wouldn't get it wrong if you wrote KMT. Yeah, no problem. All right, so the graph below shows a distribution for the molecules at 120, and we want to know what a graph would look like for the molecules at 30 degrees. All right, so what's going to happen? You got 3 choices. You can shift left, you can shift right, you can stay the same. Graph squishes is a great answer. All right, so what we're going to see is something that looks like that, all right, where this peak shifts towards lower energy. All right, so the peak of the molecules shifts towards lower energy. All right, and if we had raised the temperature, we would expect it, to shift right. All right, so if we went to a higher temperature, we would have more molecules getting to the activation energy. All right, is everybody good with that? Does anybody have any questions? Everybody good? The height would decrease. It's a Boltzmann distribution. Yes, we would shift, so it should decrease but the area should be the same. But yes, it's a Boltzmann distribution. Why would there be more collisions? Why would there be more collisions at the higher temperature? Because the molecules are moving around faster and they're going to bump into more things. All right. So, so the red one here, there's more collisions at lower energy versus more collisions at higher energy. So you have to look at the x-axis. So it's energy. All right, so this is saying that we have more molecules at low energy. So they're colliding and they're colliding at lower energy. And remember that, kinetic energy is 1/2 mv squared, right? Velocity is squared. So if I have a low kinetic energy, my velocity goes down. So kind of think like they kind of bump into each other and then release. Nothing really happens. All right, so I'm going to go ahead and put up the next set from this set of questions. All right, so here we go. So S2Cl2 is a product of the reaction, and they want us to do a Lewis dot diagram. All right, so I'll just take a minute to kind of remind everybody that what we want to do is get octets. All right, we want to follow the octet rule whenever possible. All right, and so then different columns of the periodic table like different things. All right, so I'm going to adjust carbon, oxygen, nitrogen, fluorine. Okay, so if I have carbon, oxygen, nitrogen, fluorine. All right, I'm going to tell you what an atom likes. All right, it's not what they always do, but it's what they like. All right, so carbon and its entire period likes 4 bonds and 0 lone pairs. All right, oxygen likes 2 bonds and 2 lone pairs. All right, and then we're going to note here that sulfur is below oxygen, so it's going to act like oxygen. All right, nitrogen likes 3 bonds and 1 lone pair. All right, and then chlorine likes fluorine. All right, fluorine likes 1 bond and 3 lone pairs. All right, we have neutral charges when these are satisfied. All right, and then we're going to note that chlorine is in the same group as fluorine. So we're going to try to follow these rules whenever possible. All right, and so we're going to try, and then if it works out, let me do it this way actually. So if this works out, then we'll be happy. All right, if it doesn't work out, then I have to start, playing with double bonds and triple bonds and such things. All right, but in this case, everything works out beautifully. All right, and we satisfy all the wants of the different atoms. All right, and that would be our Lewis dot structure. All right, so we try for the wants, and then if we can't satisfy them, then we have to get creative. Does anybody have any questions on that? Okay, great. What is the approximate value of the C-S-S bond that I drew? Okay. All right, so this is a Vesper question. All right, so if I let's look at the sulfur here. All right, the sulfur this is kind of acting like water. All right, does everybody see that? Water kind of looks like this. All right, 2 bonds, 2 lone pairs. Everybody see that? Kind of the same? Yes, no, maybe, kind of? All right. So let's start with something that was perfectly tetrahedral. All right, if I had something like CH4. All right, something that's perfectly tetrahedral has bond angles that are 109.5 degrees. All right, as soon as I add a lone pair, let's say I have something like NH3. All right, that lone pair takes up some space. All right, so that squishes these bonds together to 107 degrees. All right, now these two take up space, so that squishes this even more to 104.5. So this is the answer that would be perfectly correct, but they took anything between 104 to 110. So as long as you got that it was tetrahedral or in the tetrahedral category, you got it correct. All right, does anybody have any questions? Okay. All right, so I'm gonna go ahead and erase the top here. Everybody hanging in there? Yeah? All right, back to it. So CCl4 can be produced by reacting CHCl3 with Cl2, represented by this equation. Great. All right, so first of all, I want to make sure that this thing is balanced before I go any further. All right, I don't see any coefficients, so that makes me think, maybe I should balance it. So let's just do a quick check and make sure it's balanced. All right, so I'll poll the class. Is that equation balanced? Looks balanced to me. Okay, perfect. All right, at the completion of the reaction, a chemist successfully separates CCl4 from HCl by cooling the mixture to 70 degrees, at which temperature the CCl4 condenses. What does condense mean? Okay, that's a phase change. So that means that it goes from gas to liquid, all right? Perfect. Goes from gas to liquid, while the HCl remains in the gaseous state. All right, so now for part 1, we want to identify all of the intermolecular forces that are present in HCl. All right, so what are the intermolecular forces in HCl? Okay, so we always get one for free, right? You always have London dispersion forces. You get that one for free. All right, now because HCl is a polar molecule, all right, we have a delta positive on that hydrogen and a delta negative on that chlorine. So I have a dipole. All right, and so what happens is the dipole of one will interact with the dipole of another. So this is a dipole-dipole interaction. All right, so London dispersion, dipole. Did anybody want to write hydrogen bonding? Would it also be ion dipole? Really tough question, actually. So as a liquid, it is not an ion dipole. All right, because as a liquid, you assume it's together as HCl. If they had written it as aqueous, then you would have assumed that it ionized. Okay, does that make sense? HCl is a strong acid, so that is not a dumb question. All right, and we'll note here that this is not hydrogen bonding because for hydrogen bonding to occur, you need an H that's bonded to an O, N, or F. All right, and chlorine is not quite there. Okay, so now here's the tricky one of the night. What can be inferred about the relative strengths of the intermolecular forces? So I probably would have gotten this wrong if they had not given me this. All right, so that information is 100% necessary to answer this question. Okay, what can be inferred about the relative strengths? Okay, so this is, who wanted to pick HCl? Did anybody want to pick HCl? Because normally dipole is stronger than London dispersion. So that's probably what I would have gone to, but Summer just brought up the critical point here, which that CCl4 condensed from gas to a liquid before HCl does. All right, and that means, therefore, that the intermolecular forces among CCl4 are good English, are greater than among HCl. All right. So that is the end of that question. Does anybody have any questions about that question? I would say that's a tricky one. So I think I want to do, the last thing that I want to do is question 3, part A and B. All right, because it's a little different. We haven't touched on that. All right, and equilibrium is huge. All right, so I want to at least go over equilibrium a little bit. Okay. All right, and then the rest of question 3, we don't have to worry about because it's acids and bases. For the first couple pieces of question 3. All right, and then we don't have to worry about the rest of it because it's acids and bases, which is not covered. All right, so at high temperatures, and it looks like I cut off the equation, that's okay. So N2 gas plus O2 gas goes to 2NO gas, great. Okay, so now note here that they denoted Kp, so everything needs to be in pressures. And if there are units, we need to specify units. Okay, so Kp here is going to be the pressure of the products divided by the pressure of the reactants. All right, so pressure of NO and squared because the coefficients become exponents. All right, divided by pressure of N2, pressure of O2. All right, does anybody have questions about part A? Part A is pretty easy. No? Pretty good? Okay. All right, so everybody's good with that? Pretty easy? All right, let me hit the units. So this would be ATM squared divided by ATM times ATM. All right, which everybody cancels out. So we have no units on this one. You know the reaction is exothermic in the forward direction. How would you know that? What's the clue that would tell you that? I don't know that unless I'm told. So I would say in the absence of other information, we don't know. Okay, so a student injects N2 and O2 into the previously evacuated rigid vessel and raises the temperature to 2000. Great. At this temperature, the partial pressures are these, and then we're allowed to reach equilibrium. And then they want to know, we want us to calculate Kp. All right, has everybody seen ice tables? Yeah? Okay, good. So, for those of you who haven't, I guess most of you have, that's good. All right, so we set up an ice table. All right, I is initial, C is change, and then E is equilibrium. All right, so we're told that we start with 6.01 ATM of nitrogen. Again, please mute the microphones. We can hear you. All right, 1.6 ATM of oxygen, and we assume 0 nitrogen, or 0 N2. All right, and now here's the tricky part. We have to take from the reactants and move to the product. All right, minus x, and plus 2x. All right, so it's minus x because the coefficients of the nitrogen and the oxygens are both 1. All right, everybody okay with that?
Hello?
All right, and then plus 2x because we have a 2 right there. All right, so then 60.01 minus x, 1.6 minus x, and then 2x. Now we're going to use the rest of the information that they gave us in the question. They tell us the partial pressure of NO is 0.122. So that's going to let us solve for x because I know that this is 0.122. All right, so just a little algebra, 2x is equal to 0.122. And then if I divide by 2, I get x. And then I can go through and solve for the rest of my equilibrium pieces. All right, so x is then 0.061. All right, and then we can go ahead and plug that in for here. So 6.01 minus 0.61. All right, this is, let's see, 5.95. All right, and then this one is 1.55. All right, and then we go ahead and plug into our equation. So 0.122 squared over 5.95 times 1.55. All right, and then we're going to get something that's on the order of 1.61 times 10 to the minus 3. All right, and that would be our answer. Does anybody have any questions on that question? Okay. So is this reaction product or reactant driven? Does everybody know what I mean by that? Okay, so, all right, so basically I'm asking you if the equilibrium favors the products or if it favors the reactants. All right, and so in general, if you have a K that's greater than 1, then you favor the products. All right, we would say that that's products driven. And if you have a K that's less than 1, then you're going to favor the reactants, and therefore it would be reactant driven. Does that make sense? And then mathematically, you can think about like the bottom being much greater than the top. So I have more reactants. Okay, does anybody have any questions on this question? The rest of the question is acids and bases, which is not covered on the exam this year.